Hello everybody, today's video is about the lesson 4, energy escape part and LL diagrams. Some of you may have started already with the escape part simulation on the last Thursday or Friday we were in Huntington Park High School. But for this, I want you to actually analyze the energy bars or the LLO diagrams in terms of energy conversion. So we're going to take a look at that now that you actually learned about how to do LLO diagrams. So you should notice on Schoology there will be there's an energy escape part link, there's an instructions, and this is where you do the practice questions, which will be in instructions. This video will also be here soon, just I need to upload the video first, and actually I'm still making it right now, so yeah. All right, let's take a look at the LOL, energy escape part LOL diagrams, questions, and instructions. All right. So this gives you basically some instructions and then some questions I want you to answer. So right here, click on the energy escape part simulation link. I'll show you that in a bit. Then from there, go to intro for number 1 and friction for number 2. There's only 2 questions you have to fill out, by the way. All right, and make sure you're gonna click bar graph and slow motion. So for each of the scenarios, there's gonna be 2 of them, you're gonna answer these questions. I'm actually gonna show you another scenario right now to show you how to answer these questions. Actually, in fact, also let me make a new document to answer those. Okay. There's music in the background from my neighbors. Let's hope they don't hear it, but let's move on. Okay, so first question says, what are the types of energy present? And second question is, what are the parts of the system, such as one of the parts has to be the Earth? Explain the energy in the initial case. If you remember the LOL diagram, the first L is the energy that's present in the initial case, so before you start. Explain the energy in the final case, that's the last L, so that's where the energy happens at the end. How is energy being converted from one form to another? I'll go over that in an example. And write an equation explaining conservation of energy. There's also a review of the practice from lesson 3, where you have to make the LL diagram and then make that equation. So like KEI plus PEI equals KEF plus PEF, or initial kinetic energy and potential energy equals the final kinetic and potential energy. Right. So let's take a look at this. For the simulation to get there, you go to Schoology, and it's gonna be energy escape park. This is HTML5, so it should be able to work on either a laptop or a phone. And I would click on this box right here, just so it can have a bigger screen. Okay, loading. Okay, there we go. For number 1, you're gonna go to intro, and this is also where we're gonna go for the example. So let me show you where to go for number 1 and 2 first, and then I'll do, why isn't it clicking? And then I'll do an example. Okay. So for the 2 questions, you're gonna make sure you want the bar graph filled out, and you wanna put this in slow motion. And then you're gonna put this, move this around. Number 1 asks you to put in the top of this ramp, so either this position or this position, it doesn't matter which one, as long as it's in the top. And then you're gonna press play, like that. All right. And a good thing to start is actually press pause beforehand and then do it here so it won't move yet, like that. This is for number 1. So make sure you have the intro and slow motion with the bar graph, and the skateboard is on top. The final case is when the skateboard is on the bottom after you press play. All right. For the second question, you're going to want to put it into friction, which you should see down here. Then you want to again put the bar graph, slow motion, pause it. And you're going to do the same thing, except now there's going to be friction. So there's going to be the energy bar graph, or the LOL diagram is going to look different here. All right. Let me show you an example that's not one of the questions I gave you. So I'm going to say we're started from this point. around, let's say, a quarter of the ramp. And then at the same time, we're going to put it down here in the center. So let's answer the questions together. What are the types of energy present? So right now I'm at intro. So there'll only be potential and kinetic. Potential from how much it can move starting at that point. So how much it can move down. So gravitational potential. So potential from gravity output. And kinetic from its movement. Remember, kinetic energy depends on the movement of the system. All right, what are the parts of this system? So one has to be the Earth, so we know it has to be Earth. And I'm not going to give you all of them because this is really the same thing for each of them. So just to give a hint, another one should be the skateboarder. So put skateboarder and one or two more. Right. Explain the energy in initial case. So the first L, the LO diagram. So the initial case is before we pause it. So let me put that back here. So we can see that the potential energy is the same as the total energy, but they're pretty low. So we can write that. There is a potential energy and it's equal to the total energy for right now, or just right there. And then it's pretty low because we're only around a fourth of the way up the ramp. Okay. D, explain the energy in the final case. So for that, we're gonna wanna press play and let's try to stop it at the middle here. That should be good. Oops. That came out a little wrong. Stop it right there. Okay. So you can see that right here, the kinetic energy is now equal to the total energy. So in the final case, the kinetic energy equals the total energy. But the total energy did not change. Let's show that again. So if you go here, look at the total energy, just keep on looking on it when it's going down the ramp. You can see that it did not change at all. Okay, E, how is energy converted from one form to another? So we have potential energy at first and then kinetic energy afterwards. So how did that change? Well, I'm just going to PE. The PE changed completely to kinetic energy because what caused it to move? It was gravity caused the skateboarder to move down and caused it to move, have motion. So the gravity caused the skateboarder to move down the ramp. Then there is no potential energy at the bottom. And why is that? Why would not be potential energy here? Well, it's because there's no height for the potential energy there's no height to account to the potential energy. So basically, at this point right here, the skateboarder cannot move any more down, so there's no more potential for it to fall. So the skateboarder at the bottom of the ramp has no more height to move down, so there's no potential for it to fall, meaning no potential energy. So there's no I'm going to put not. There's no PE at the bottom because there is no height for the skateboarder to move down, leaving only kinetic energy. Now that's not the case when we continue forward, because watch if I do this, or we stop right here. Right here it's moving, the skateboard is moving, and there's potential energy because it's still falling, so that's why it's a little bit of both. The sum of these will equal the total energy. Okay. Okay, and then it says writing equation explaining the conservation of energy. So let's do the equation tool. You don't have to make an equation just all nice looking here. Just you can just write KEI, PEI, KEP, PEP, KEF, PEF. I'm just making it here to make it look nicer. So when we started, we only had potential energy. So let's say the initial case. Remember, EI equals EF, where EI is the initial energy and EF is the final energy. In the initial case, there was no kinetic energy, only potential energy. So let's put that PEI, and then there's no kinetic energy. So we just leave that. At the end, there's only kinetic energy and no potential energy. So at the end, there's only KEF. That's the entire equation, just this. PEI equals KEF. So initial potential energy equals final kinetic energy. In this case, when there's no friction. Okay. So this should help you get should help you get started for the other ones. The number one this time asks you to put in the top of the ramp, and then number two this time tells you to do the same thing, but this time you want to click the friction thing down here. All right. Should be everything for this lesson. Just make sure you work on this simulation and just help you prepare you for having more practice for LLL diagrams and then calculating and developing an equation for conservation of energy. All right. Goodbye, everyone.